Not that I'd mind. Hopefully we'll get more. All right. Section 9.2. So look, we have this section in chapter 9 left, and then we have chapter 10, and then we're done with new material. And chapter 10 does a lot of chapter 9 stuff, and it just kind of adds another little piece to it. So it's not super complicated. So today we are going to look at means. So section 8.1, that material will be useful for 9.2. We're going to look at point estimates for population means. We're going to look at something new called a t-distribution, and I'll explain what that is and why we use it and all that stuff. And we're going to do confidence intervals for population means. On Tuesday, we did population proportions. Today, we're doing means. And then we're going to also learn how to find a sample size to estimate the population mean with a specific margin of error, just like we did with proportions, just with means today. Then after that, we're going to go through the lab. The lab should be super quick. It's using tools that we already have used. And hello, Elena, I see that you just arrived. So we're going to use tools we've already used before. Let me think of which lab it was. I think it was lab 3. Might have been lab 3. Lab 2 or lab 3, one of those two. Those were the same week, so it kind of throws me. So whichever one was not the linear regression one, that's what we're going to do. We're going to use the descriptive statistics box that we paste in there. We're going to do that as well. So that's today, and we'll get started. It really shouldn't take that long, especially since we've done a lot of this before. We did a lot of this Tuesday, and we're just switching it up and using the mean instead. And I want to apologize in advance. My dog is being extra annoying tonight because he is soaking wet from being outside. So he's trying to lick all the water off his whole body. So I'm apologizing if he makes lots of noise. All right. So we used a point estimate with proportions, and that was our p-hat. Our point estimate with means, that is just the sample of the mean of whatever the sample is. And we use that sample mean to estimate the population mean, because sometimes we don't know the population mean. And if we have the population mean, we don't need a confidence interval. So it's just kind of pointless. So we need to use our point estimate from our sample, which would just be our X bar. All right, so I have a bunch of data here. This is a long time ago, long time ago in chapter 8, we had a bunch of pennies. This is a sample of those pennies. So we have 17 randomly selected pennies minted after 1982. So we are going to estimate the population mean of the pennies after 1982. So our point estimate is just going to be the average of all of these numbers. I'm not going to make you do it. I feel that you probably can. So we just take all of those data values and add them together and then divide it by 17, which is the number of pennies in our sample. So our point estimate, our X bar here, is 2.464 grams. So that's the average of that sample. And we generally round our sample statistics to one more decimal point than the raw data. So if our raw data is 2 decimal points, we round it to 3. If it was 1 decimal point, we'd round it to 2. If there are whole numbers, round it to 1, if that makes sense. All right. So a t-distribution. So if we take a simple random sample of size n, and we know that the population follows a normal distribution, we have to calculate a t-value, which is very, very similar to a z-score. And I'm going to explain in a few minutes exactly what the difference is. So our t-distribution, we take our X bar, so our sample mean minus our population mean, and then you divide it by the new standard deviation. So remember, this was the standard deviation of our sampling distribution. So we're dividing it by that. The reason we have an S instead of a sigma is because, as I said, we only have sample data. we don't have our population data. So we'll take our sample standard deviation and divide it by the square root of n. Remember, n is our sample size. So this gives us a t-value, which is almost exactly the same thing as a z-score. And I will explain this n-1 degrees of freedom in a moment. So give me a moment on that and I will explain what it does. All right. Uh-oh. Sorry about this. I hate when this happens. So for some reason, sometimes my symbols get lost. Oh, this should be sigma. So for our z-score uses either the population standard deviation or it uses larger sample sizes. T-distribution uses sample data and because we don't have the population data and we have smaller sample sizes. I'm going to draw the histogram for both of them and you'll kind of get an idea of what it looks like with the different ones. They're going to look pretty close to the same. So we're going to start with a sample size of 5. So here we go. So this is a histogram for our z distribution with our sample size of 5. You can see that it is mostly normal and it's pretty close to bell-shaped. You might be able to, you almost could call that bimodal because it does have this little spot right here. You can almost call that bimodal, but it is, I mean, it's mostly normal. Let's take a look at our t-distribution. Maybe, if I can get there. Here's the t-distribution. The t-distribution is more normal. However, our tails do go longer. Our tails go longer, but you can see that the curve, the bell is a little bit better with our t-distribution. And this is because our sample size is 5 and we use a smaller sample size. A t-distribution is the better model. I am not going to test you on the difference between a t-distribution and a z-distribution. Don't worry. I am not testing you on those things. This is just kind of trying to get you a little bit of an understanding. And it is kind of ambiguous. It's not super clear, but I'm going to do the best I can. Okay.
Quick question.
Uh-huh.
It's a rule that the t-distribution always uses sample data?
Yes, because the thing is we're pretty much always using sample data when we're doing confidence intervals, because if we have the whole population, we don't need a confidence interval. And with when we were doing last week or on Tuesday, when we were talking about proportions, we had kind of an estimate of the population proportion. And so we were using that, or we had our p-hat, but we still only had sample data. But when we calculate z-scores, most of the time we're trying to look at a population. And with t-scores, we usually have small sample sizes. The sample size is our biggest indicator of when we use a t-distribution. And it's anything less than 30 most of the time. But in this case, in our class, you are going to use a z-scores for proportions, t-scores for mean. And it's just kind of how it worked out. If you go on to Math 244, so if you go on to the next class, then they'll probably narrow it down a little bit more for you. But for this intro class, z-scores are going to be for your proportions, t-scores for your means.
Got it.
I'm just going to keep them separate.
Okay.
Okay. So notice our histogram for Z is symmetric and bell-shaped, center of distribution with it at 0. All of our rectangles were between -3 and 3. It did follow mostly a standard normal distribution. The t-score was symmetric and bell-shaped. Our center was 0, but as you noticed, our tails were longer and more dispersed. It says it's unlikely it follows a standard normal distribution because it was bell-shaped, but our tails were kind of long. It looked a little bit more spread out. And the reason is because we're using sample data to find the t instead of sigma. We're using a sample standard deviation instead of a population standard deviation. I mean, the only standard deviation we used with proportions was based on the p-value. So we didn't even deal with the standard deviation of the data. We just calculated that with our p-hat and our sample size. But when we're dealing with mean, we have to have some standard deviation, but we don't have a population, so we have to use sample. I know that's a lot of words. But we do have more dispersion in a t-distribution, but it's perfectly fine. It is okay. It is expected. It's why we use the t-value. Okay. Once again, a lot of words. T-distribution is different for different degrees of freedom. Degrees of freedom is just basically your sample size. It's a little more complicated than that, but we're just going to just call it sample size. Don't go any deeper. So in our case, degrees of freedom is your sample size. Our t-distribution is centered at 0 and is symmetric about 0. You're not being tested on this. I'm never going to ask you to repeat this, just giving you an idea. The area under the curve is 1. 50% is to the left of your mean. 50% is to the right of your mean. As my t-value gets super, super big or super, super small, the graph is going to approach but never touch 0. In previous classes, you may have heard the word asymptote. An asymptote is a line that they can get close and close and close to, but you can't touch. And so our 0 or our x-axis would be that asymptote. Gets really, really close to 0, but it'll never touch it. Okay. The area in the tails is slightly greater than the area in the tails of a standard normal distribution because we're using a sample. There's a little more variability in a t statistic. As our sample size increases, we get closer and closer and closer to a standard normal curve. Because as our sample size gets bigger, our sample standard deviation is going to get closer to the actual standard deviation. Once again, this is just explanation. You'll never be asked this information. But it's interesting and it's good to know. And I like to know this stuff, but I'm weird. I'm a math teacher. Okay. All right. So take a look. The normal curve is the blue. Our smaller sample size is this orange one right here. And it's more spread out and it takes longer for it to get to close to 0. The red one has a 15 sample size and look how it gets closer to the normal. So we get about normal at about 30. 30 is where we hit about normal. And you may recall on your last quiz when we were talking about sampling distributions, when it asks about when is a sampling distribution normal, and it's normal if the population is normal, but it's also normal when our sample sizes get greater than 30. And that greater than 30 is the magic number here as well. Once our sample sizes hit about 30, then we have a normal curve. Okay. So just like with our Z values, we have T sub A or sub alpha. So we use the T value with the sub alpha. The alpha is the area under a standard normal curve to the right. So this area right here to the right of my T value, this is alpha. Man, all sorts of weird things are happening. I'm wearing a sweater and every time it touches my iPad, it makes the iPad do funky things. And I keep pulling it up, but the sleeves are too wide, so it falls back down again. So I'm trying, I'm just on the struggle bus here. So this area right here would be your alpha. So it's basically whatever this big percent is here, 100% minus that. We kind of did a little bit previously, but this would be one side of this would be alpha. Now, if I had both sides of it, then we would have alpha divided by 2. I probably have that. No, I don't. So if I had both sides of it, then I would have T sub alpha divided by 2. Both of these would be divided by 2. And then so each area would be half of that alpha. If we're dealing with the center, like the center percent, then we've had alpha divided by 2. That makes sense. Okay. All right, come on, come on. All right. So our T value, Sammy, stop it. Okay, we're going to find the T value such that the area under the T distribution to the right of the T value is 0.2. We're assuming 10 degrees of freedom. Okay. So I'm going to show you on my T table. Do I have a T table on here? I do. I don't like that T table though. I'm going to show you your T table. If we go over to our, hold on a second, the tables that we have, we've only used the Z table so far. Let's scroll down. The second page is your T table. Okay. So my T table here, on the left is our degrees of freedom. This is our sample size, is our degrees of freedom right here. And then up here is our alpha. At the top is the alpha. We're looking for the T value that corresponds with alpha 20 and 10 degrees of freedom. So you go down here, I'm gonna make this a little bit bigger if it'll let me. Okay. Woo, I went too big. It's okay. Go big or go home, right? Okay, so we have our degrees of freedom 10 right here, and then go over to our 0.2, which is the area we're looking for. So our T value for 10 degrees of freedom with an alpha of 0.2 is 0.879. This only gives me the right. This only gives me the area above, area to the right of that. I didn't cut it in half, just gives me the area to the right. So that area is 0.879 right there. So that's my T value. That's just like a Z score, but we're just using it in this case because of the mean and the small sample size. So let me go back to that other page. So in their table, see, their table looks a little bit different than mine, and that's why I didn't use it, because theirs is a little bit weird. So here's mine right here, circling it on their table. So we have 0.2, 0.879. So that is the T value, T sub 20 or 0.2. So when we are looking at T values, and this is probably on my next screen, when we are looking at T values for our sample data, we are going to use n-1 degrees of freedom. We will always subtract 1 from our degrees of freedom. The reason for this is because of the fact that we're using sample data, we have to kind of, we need a little bit bigger margin of error to account for the fact that we have a sample. Because there's so much variability in sample data, we want to kind of give some wiggle room. It's the same reason we divide by n-1 when we're calculating sample standard deviation. Because there's that variability there, we need to kind of account for that by subtracting 1 from our sample size when we're finding our T value. It's going to give us a slightly different Z score or T score, which is fine, because this would have given me a 9 instead of a 10, or it would have given us 0.883 instead of 0.879. So it just accounts for that variability a little bit. So it actually gives me a smaller T value. It's okay. This is what we do. That's bigger. Man, I cannot even read or math. It's a little bit bigger, not smaller. Ignore me. Okay, let's move on. All right, so we're going to find the t-value such that the area under the t-distribution to the right of the t-value is 0.05. We're assuming 15 degrees of freedom. So I'm going to show you the t-table. I'm going to zoom it in just a little bit. We're going to get 0.05 and 15 degrees of freedom. Okay, 0.05 is right here. Let's go down to 15 degrees of freedom. So right here, my t sub 0.05 is, okay, 1.753. The t-table is beautiful and wonderful and great. However, there will be times when they give you more difficult t-values to find. So I'm going to scroll. Give me a second here. So notice how my t-table, after we hit 40, it jumps by 10 at a time. So if they gave me 45, I can just half the difference between 40 and 50, and that's all well and good, or I can estimate. But I'm going to show you how to do this on the calculator, even though I do really like the table. Oops, I just went too far. So let's once again do the with 0.05, 0.05 as my alpha, and 15 degrees of freedom. So second vars, we're going to do inverse t. It's right under inverse norm. This inverse t right here, if you have an alpha and a degrees of freedom, it will give you your t value. So inverse t, right there, and it asks for your area and degrees of freedom. So my alpha is 0.05. My degrees of freedom were 15. And I'm going to hit enter. I will paste. And it gave me negative. It's because it doesn't think about the fact that I want the top. So we just have to know it's positive, know we're looking at the top, but it's 1.75 right there. I think it wanted me to do 0.95, but you want the positive. We always want the positive when we're dealing with doing these. So just know you need the positive. So remember though, if we're looking for t values for our confidence intervals, we always do n-1 degrees of freedom. So I would have put 14 in here had I been looking for a t value for a confidence interval. So that's second vars, and it's inverse t, which is right below inverse norm. Questions yet? Okay. All right. Okay, here's how we construct a confidence interval for mu. So sample data comes from simple random samples or a randomized experiment. It should tell us if it's random. If it's not random, we will assume it's random. Our sample size has to be less than 5% of the population. And either the population needs to be normally distributed or our sample size needs to be at least 30. So they should tell us that. Now, just assume every question I give you has that. Just assume all of it comes with that, all right? So we need a confidence interval for mu. So once again, this is just like we did the z-score times the standard deviation. Our margin of error here is your t sub alpha divided by 2 times the standard deviation. That's the new standard deviation, that's standard error. And we use n-1 degrees of freedom when we are finding our alpha, or we're finding our t value, which is also a critical value. If my open math asks you for a critical value, that's what it's looking for. It's looking for your t value with n-1 degrees of freedom. All right, we all ready for this? Our calculator.
Sorry, I didn't catch it. Will you go back just one and sorry, just forward.
Oh, okay.
And so X bar is our sample mean.
Correct.
T is what we're dealing with right now.
T is like the Z-score, but with T-score.
T, and those are our wings because it's divided by 2.
Right.
Then S is the sample
Yes, sample deviation.
standard deviation.
Yeah.
And then N is our whatever population we're dealing with.
Yeah, this is from our sample, whatever sample we've taken, we find the standard deviation of that sample. And then this is our sample
Okay.
size. There we go.
Cool. And then you said if my open math asks for critical value and that bottom line, this is what we're looking for.
Yeah,
And
it's
this is the
T-score
formula
with-
we use.
Yeah, well, the critical value is the T-score with n-1 degrees of freedom.
Okay.
So basically, you're just subtracting 1 from your sample size when you calculate your T-score.
Okay. Okay. Yeah. Thank you.
No problem. Okay, I have some sample data right here. For this sample, we have a standard deviation of 0.02 and a sample mean of 2.464. This is the sample we did before. We want a 99% confidence interval about the population mean for the weight in grams of pennies. So these are our numbers. Thankfully, I'm not making you calculate this. You will, however, in your homework, and I'm going to show you how to do it, you're going to need to put those into your L1 in your calculator and do some calculations. Because some of the questions will give you a mean and standard deviation. Some of them are going to give you data. So we'll go over it again so we can practice that. Okay, so the first thing that we do is we calculate our T-score. I'm going to go, so we're looking for 99% confidence interval. So you would do 1 minus 0.99, which is 0.01. Then we divide that in half. That's 0.005. So this is the value we're going to look at on our T-table to get our T-score, 0.005. And we have 17 data values. So you're going to look at 16 for the degrees of freedom and then 0.005. I'm going to jump over to that screen just a second here. Okay. So we're going to go to our tables and we're doing 16 degrees of freedom. So there's 16 degrees of freedom right there. And I go over 0.005, which is way over here. I have 2.921. Can y'all see that? You can make that a little bit bigger. Maybe make it a little bit bigger. There we go. So 16 degrees of freedom, 0.005. I have 2.921 is my T-score. If I was using my calculator, I'm going to do inverse T. I'll get there again. Okay. Second vars, inverse T. I would put 0.005 and then 16. Whoa, that's not a 16. 16. It'll give me a negative, but that's okay. We just know it's positive. It gives me negative 2.92 rounded to 2.921. All right. So that's my T value. Whoa, stop it. That darn sweater. That's my T value right here. So I'm going to take the T value and multiply it by the standard deviation. So I have 2.921. The sample standard deviation that I have is 0.02 divided by the square root of 17. This is your actual N. It is not N minus 1. This is your actual N. So as you can see, my margin of error is right here. But I'll put M, capital M, capital E. That's my margin of error. And we add that and subtract it from our mean in order to get our confidence interval. So we will either answer the question like this. Or they'll ask you to answer it like this. Or they'll give you two separate boxes to put it in there. Either way. So we're 99% confident that the mean weight of pennies minted after 1982 is between 2.450 and 2.478 grams. This is the way you would answer the question after you found your confidence interval. I'm going to be pretty lenient on grading on that. As long as you communicate it well enough that I know what you're talking about, I'll be pretty lenient on that. I'm not super strict about phrasing if I understand what you're talking about and you've covered everything. Questions on this before we do another one where we actually math it out together? It's not a whole lot different than what we did with proportions. Just a couple little tweaks here and there. All right, let's do another example. Okay, so the website fueleconomy.gov allows drivers to report miles per gallon of their vehicle. The data below shows the reported miles per gallon of Ford Focus automobiles for 16 different owners. So this is a sample, and it says it's a simple random sample of all Ford Focus automobiles. We're going to construct a 95% confidence interval for the mean miles per gallon of the 2011 Ford Focus. Okay, so I am going to put all of these into my calculator into the L1 so that we can use one variable statistics to get our mean and standard deviation. It's been a little while since we did this, so this is good practice. Let's go to our calculator. I'm going to clear all this out just because it looks messy. So go to Stat, and then you want the first option, Edit. I've got lots of stuff in my boxes here. So if you highlight the L1, turn it black, and hit Clear Enter, it'll clear your entire column. So I'm going to enter these values in. 35.7, 37.2, 34.1, 38.9, 32, 41.3, 32.5, 37.1, 37.3, 38.8, 38.2, whoops, 38.2, 39.6, 32.2, 40.9, 37, 36. I'm going to quickly scroll up, make sure that I got all those numbers, that nothing looks weird. Okay. If you still need, I'm going to give you a second if you're copying my numbers and still need a second. Oh, there we go. Okay. All my values are in there. Hopefully yours are in there too. Now we're going to go to one variable statistics so that we can get our mean and standard deviation. So once again, you hit Stat, arrow over to Calc, and we want the first option. That's one variable statistics. L2 should be blank, or frequency list should be blank. We just want the list in L1. Frequency list should be blank. Hit Calculate. There we go. So the sample mean is the exact same thing as population mean. They're both calculated the same way. So here we have an X bar of 36.8. Then our SX, the S or SX is our sample standard deviation. So it's 2.92. So we're going to use 36.8, and actually I need to go one more, there's not one more decimal, and 2.92 is my standard deviation. Make sure you are grabbing the sample standard deviation and not the population. You want the SX. Does anyone need another moment or are we okay? Okay. All right, let's go back over here. All right. I always like to calculate my my margin of error first. So we need our T value. So I'm looking at a 95% confidence interval. So I'm going to do 1 minus 0.95, which is 0.05, and half of that, 0.025. This right here is what we're looking at. This is our value that we're going to look at the top of the T-table. And we have 16 data values. So we're going to use 15 degrees of freedom. So 16 data values is 15 degrees of freedom. Let's go over to our T-table. Okay, so we're at 0.025. Here's my 15 degrees of freedom. Head over 0.025, 2.131. So my T sub alpha divided by 2 is 2.131. Y'all see that? So it's 15 degrees of freedom over here to 0.025. So it's right there. I'll do it on the calculator also, just so we can all see it. Second vars down to inverse T, 0.025, 15 degrees of freedom. I know it shows negative, but we know it's a positive. It's the same number, 2.131. We better get the same number. Otherwise, we have issues. Well, I mean, we might have issues anyway, but we'd have different issues. Okay. All right. Now we're here. Got all my stuff right here that I need. I'm going to change colors. I've got everything I need hanging out right here. So I don't have a ton of room here. Hopefully you have more room on your paper. So my margin of error equals our T value, 2.131 times 2.92 divided by the square root of 16. This is how we calculate our margin of error. The T value times the new standard deviation. I'm just going to use my hand calculator here. I think we can all math this out without me putting it on the screen. I hope. If not, you let me know. No, maybe I can't. I just accidentally deleted everything. There we go. Did y'all get 1.56? Oh no, I did it again. My iPad does not like it if I accidentally bump the cord. Rude. Okay, come on. And it navigate away and navigate back. Oh, there we go. Cool beans. Okay, did we get 1.56?
Yes. Yes, yes, yes.
Yay! Yay! I don't always trust myself with the calculator, so thank you. Okay, so the ways that we can write our answer here is we could say our mean is, what is our mean? 36.8. So we could say 36.8 plus or minus 1.56. Now it's not showing up. What the heck? Okay, give it a minute. Why? I'm gonna try this again. Let me see here. Okay. I don't know why it's doing this. Is it there? Come on, come on. Darn technology, right?
Yeah.
Who needs it anyway? I mean, we kind of do, but let's see. It made noises. See if it likes me. There we go. Yay. Okay. I hope it works. Okay. Or I can add that 1.56 and subtract it. So I'm going to do that right now. So 36.8 minus 1.56. That's going to give me my lower level. 35.24. And then the upper is 36.8 plus 1.56. That's 38.36. So you would say that we are 95% confident that the actual mean miles per gallon of Ford Focus automobiles is between 35.24 and 38.36 miles per gallon. And I don't think that it's asking you to write out your conclusions so much. I don't know. I don't remember. But if you just say something about being 95% confident that the average miles per gallon is between those two values, or if you said is 36.8 plus or minus 1.56, I will accept that. Do you have a question?
No, I was just gonna say there is a writing portion on some of those questions.
And I manually grade those. Even though
Yeah.
it gives you a grade for them, it looks for like certain words.
Uh,
It'll give you full credit, but I usually go back in and read it just to make sure. Because every once in a while, somebody will just type in like the keywords and not actually answer it. Believe it or not, it happens very rarely, but occasionally it happens. Somebody's like, oh, they want me to put 95% in here. And I know that it needs to say average in here or mean in here. And the computer looks for certain words, but can't like read it for context. So I kind of go through and just look at them, but it's pretty rare that anybody's wrong. I'm really lenient on that. If you have the basics there, it's good. I'm going to show you though how to use your calculator now. So I'm going to erase this. It is going to be T interval. This one is like super, it makes more sense than one prop Z int. Okay, why is it doing that? So it's T interval. Let's pop over to the calculator. All of our values are still in there, which is super cool. So everything is already in my edit screen. So if it wasn't, I'm going to erase 2 just because I don't like it there. So if your data wasn't already in here, you would enter your data into the L1. Oh, I just erased. No, okay. Okay, if it wasn't already in there, you would enter your data into the L1. Now you're going to do second vars. Now I just lied. Hit stat and go over to tests. And we want T interval, which is number 8. So go all the way down here to number 8. Hit enter. So there's 2 different options here. So data is if you have stuff in your L1 column. Stats is if you only have, if they gave you a mean and standard deviation and you want it to calculate it based on statistics. Notice here, because we'd already run stuff with our data, it's already entered in here. But anyway, so we're going to use the data that we just entered in, and our data is in L1. Frequency, we don't need anything in there. Oh, it requires me to have 1. So just put 1 in your frequency list if it's not already there, where it says FREQ. So we're just counting everything one time. My list is L1. My confidence level is 95%. So put that in there. Go down to calculate. And notice it gives me this is basically what we had, isn't it? I erased mine, but I think that's basically what we had. I can look on my other calculator. Yeah, we had 35.24 and 38.36. So super, super close. Ours involved rounding. The calculators did not involve rounding. So it is definitely close enough. So let's say you were given the mean and the standard deviation. I'm going to go back to my T interval. Let's go back to the tests. So T interval. Let's say I'm given a mean and a standard deviation. I'm given the mean of 36.8. I'm going to put this as our rounded number, 2.92. So we have our rounded number, our degrees of our N is 16, 95%. So this is the data that you're given. So you weren't given a list of all of the data values. You're just given the mean, the standard deviation, and you have the number of your sample. Hit enter. And once again, it will give you your interval here, which is exactly what we got. So depending on what you're given, it can calculate both of them for you. Any questions? All right. So sometimes we need a sample size. This is exactly what we did yesterday. But the problem is that our T value is dependent on our T value is dependent on knowing your sample size, but we don't know our sample size. Therefore, we have to find a Z-score. We have to use the Z-score because we don't have a sample size in order to find a T value. That makes sense? So kind of like what we did with our, when we were estimating our P hat, because we didn't have a P hat yesterday or Tuesday. So same thing here. We have to use a Z-score for an estimate because we don't have a T value. So you take the Z-score, multiply it by the standard deviation, divided by margin of error, and then square what you have. This will give you your sample size. Now, N is, you always round up, just like before, just round up to the next whole number. We're going to use this formula. Hopefully it'll help. Okay, back to the pennies. We want to know how large a sample size we would need to estimate the mean weight of pennies manufactured after 1982 within 0.005 grams with a 99% confidence. We're assuming a standard deviation of 0.02. So once again, if we don't already have a sample, we have to have an assumed standard deviation based on whatever. Maybe it's a prior sample or something. They'll give it to you. Don't worry. So I'm going to go back to my Z table just because it gives me the Z score for 99%. So my Z score, oh, I hate when that happens. My Z score for 99%, I'm going to write this down on my screen, is 2.575. So that Z score for 99% is 2.575. So the Z score is what we're going to be using here. So I'm going to take the, in parentheses, I'm going to put 2.575, which is my Z score, times the given standard deviation divided by my margin of error, and then square it. Be really careful with parentheses. In your calculator, you are going to want to put parentheses right here and parentheses around the whole thing. So I'm going to do that right now. Go ahead and calculate that and see if you get the same thing I do, because I don't trust myself. How'd we do? Do we get the same value? Okay, I'll give you a moment. Yep. Okay, good.
Yes.
Woo. Okay, so remember, we always round up. I know this is practically 106, but we can't accept that. So our sample size, our N would be 107. We would need a sample size of 107 to get a margin of error of 0.005 and a 99% confidence. Questions? Okay. Hey, look at that. Imagine that. I didn't even know that was there. You think I would have. All right, let's do one more. We'd like you to try this one. So back to miles per gallon of Ford Focus. How large of a sample size is required to estimate the mean miles per gallon with a 0.5 miles per gallon within 0.5, 95% confident? I'll get you the Z-score. The Z-score is 1.96. I'm trusting that you can get a Z-score by now, so. Uh-oh, that's not the screen we want. All right. So go back to what our standard deviation was that we got. Is it 2.91? So we had a standard deviation of 2.92. So let's use that. Uh-oh, that's not right. So we have our SX equals 2.92. So use that as your standard deviation. I'm going to work quietly behind you. All right. Did we get the same answer or did I mess up?
Yeah. Well, oh, you round up even if it's just so
Yep.
slight like that? Okay, yeah.
It does not matter because
Yeah.
technically 131 is not enough.
Okay.
So yeah, even the slightest, this little bit over it. I know it's kind of annoying, isn't it?
It's just weird.
Yeah, it is. We always round up to the next value. Now, if I had 131.0000001, I probably would just use 131. But technically, if you are over that amount at all, you round up.
Okay.
All right. So I'm gonna do a comparison of Tuesday and today a little bit to kind of separate the two different things because this is it on and then we're gonna do the lab. So 9.1. This is the way the question would look. This is how the question would look. Obtain a 90% confidence interval for the proportion of registered voters who are in favor of the death penalty for person convicted of murder. Man, I can't speak. So you're going to see the word proportion in there. And this is where you're going to use Z-scores and you're going to use that funky standard deviation where it's p hat times 1 minus p hat or square root of p hat times 1 minus p hat over n, that funky one there. That's section 9.1. Here, you see I have the word mean in there. So construct a 95% confidence interval for the mean miles per gallon of a 2011 Ford Focus. So this is what we did today. You will see the word mean in there. And this is that standard deviation divided by square root of n to get the standard deviation we need, plus its t values. So this is t values. And this is this right here. And this is z scores. And this right here. So those are the differences.
Would you also mention which calculator functions are associated with?
This is, I want to say that the Z one, I frequently say it slightly off, so I'm going to go down to it so that I have it's okay. It's one prop Z int. And then this one is just T interval. And then that you would use inverse norm to get your Z score. And you'd use inverse T to get your T value. And then I'm going to do this. N minus 1 degrees of freedom. Does that help?
Yes.
Okay, good.
Big time.
Good. All right, I'll let you write all that down.
Good, good.
Okay, good. And then sample sizes. So it would say something like what sample size should be obtained if you want to be within 3 percentage points. It'll be always ask you like percentage points. And then might say something like you had a previous survey of 82.4% or something like that. Somewhere in there, percent will be mentioned. And this is the previous, the P times 1 minus P hat. And then it is Z over E squared. This is how you would find your N. And then this one right here, you're going to see the word mean in there. And your, whatever they're wanting your margin of error to be, it's going to have the units will be similar to what your average is. So your average is going to have units. Your margin of error is going to have units. And then this is looks like that. That's really ugly. I'm sorry. There might already be a document also in this week's materials. I think there is, but it really helps just to put it in the lesson so it's with your notes. And that's it. Let me know when you're done, then we'll do the lab.
Okay.
All right. Elena, are you good? You good to go on the lab?
Yes.
Okay, just making sure. All right, so let's do the lab. So this is lab 5. I just used my continuous data from way back when, from the first lab. This is from the very first lab. I got my continuous data from there, and I believe we used it again on lab 2. And so I just got that continuous data. You are more than welcome to grab your data from your final project, one of your variables, if you'd like. I don't care. Use whatever you want for your data. You're not going to be judged on what the data is that you grabbed. But you never know. You might want to decide to throw confidence intervals into your final project, and you can use this lab to help you with that if you wanted to. So, all right. So we back on, I believe it was lab 2. I could be wrong, could have been lab 3. we used our descriptive statistics. We're going to be using that again. So if you click on the data tab, hopefully your data analysis tool is still activated. If it's not, you're going to have to go back to whichever lab that was. I believe it was week 2. I'll check after we're done here. And you're going to need to look at those instructions again. Okay, so I'm going to click on data analysis tool. And I want, once again, I want to do descriptive statistics and click OK. My input range is going to be all of this continuous data. And I regret every time that I have 5 million data values. Thankfully, it's still quick. Ooh, I went too far. I went too far. It happens all the time. I get overly exuberant. Things happen. All right. So the things that I want my output range. I want it to go in this little box right here. Wherever that is, I want that to go into that box there. You're going to click on some different things here. I do want my summary statistics, but I also want the confidence level. So right here, we have confidence level for mean. I'm going to click on that box, and you can put in whatever percent you want. If you want a 95% confidence interval, you're going to put that there. If you want your confidence level to be 99%, you can put that there. If you wanted it 86.5%, you probably could put that there. Whatever confidence interval, confidence level you want to do, put it in there. It defaults to 95. You could do whatever you want. And then I'm going to click OK. And it's going to paste my descriptive statistics here. I'm going to make them bigger. So all of the stuff we had before is here. But this right down here is the one we want to look at, this highlighted here. Even though it says confidence level, this is your margin of error. Let's see if I can make it bigger. This is confidence level 95%. That's your margin of error right there. So I'm going to click in this box right here, and I'm going to put equals and hit that to get the margin of error in that box. Yeah, I know you know how to find the mean. We're going to hit equal. Click on the mean and hit enter. My lower bound is going to be my mean minus my margin of error. So I'm going to put equals this number minus this number and hit enter. And it's going to give me my lower bound. My upper bound is going to be equals this number plus this number and hit enter. And that gives me the upper bound. This is my 95% confidence interval. So the interpreting your results down here, this 1, 2, and 3, it kind of scaffolds. So basically you're typing in one small piece at a time, and then you put it all together in the bottom. What we are estimating here is we are estimating a population mean. So whatever your data is, you're going to say, I'm estimating the population mean. Mine's earthquakes. So I'm estimating the population mean of earthquake magnitude in the whole world. So you're estimating a population mean. So if you collected, let's say you collected temperatures, I'm estimating the mean temperature for the city of Medford, whatever you're doing. I don't know. I'm making stuff up. So you are estimating a population mean, whatever your data is. So make sure you talk about it in the context of what your data is. How confident are you? All you have to say is 95% confident. Or just type in 95%. That's asking you, what's this confidence level? That's all you need in that box. If you want to give me more, go for it. But make sure you tell me you're 95% confident. Where you are going to write your entire interpretation is right here. So I would say, I am 95% confident that the mean magnitude of earthquakes in the world is between 6.86 and 7.23. That's what I would say. You may need units for yours. Earthquake magnitude doesn't have units, but if you were doing temperature, you would say it's between this degrees and this degrees Fahrenheit. Or if you're estimating amount of money spent per month on electricity, you would say it's between these many dollars and these many dollars. That's it. That is the entire lab. And I just did that in like 2 minutes and I was explaining it. So you could do it pretty fast if you already have data. So questions?
So the 95% is implied. I don't see it anywhere over here.
Okay,
in the
take a look.
report.
So it's right here. It's what I typed in the
Oh,
box.
there it is. Gotcha.
Right.
Okay.
You,
Okay.
you choose that confidence interval when you're clicking all the boxes to paste this in here.
Yeah.
So I chose 95%. It was the default. It will default to that unless you choose something else. You can
Okay.
choose whatever you want. If you want to be 2.5% confident, you absolutely can, but I don't know why you would. I mean, it might be amusing. I probably would chuckle. Any other questions?
I have questions, not about this, but about the.
All right, so do you want to wait till you're off screen or do you want to ask them on
Maybe I'll ask just in case it does benefit somebody
Okay.
else.
All right.
So what we've learned here today is any of this going to apply to our final project? Any of these formulas?
If you want to, yeah, I mean, you totally could. You could say, you can, if you wanted to predict the population mean of something you're doing, there's no reason you can't. If you're
Okay.
trying to figure out what the actual average might be, because you never know. Like, I want to calculate what I think that the average number of cups of coffee that people drink is between these two values. You could. I've had people construct confidence intervals before. You don't have to. It is not necessary.
Okay.
If it fits within the scope of your data or you're just curious, go for it.
Okay.
Even if, because sometimes people calculate things that don't apply to their big overarching question.
Mhm.
But as long as you, in your paper, if you said, I was just curious where the actual population mean might be, therefore I constructed this confidence interval and it looks like it's probably between these, or I'm 95% sure it is between these two values.
Okay.
There's no reason you can't.
Okay.
And sometimes it just adds something interesting, even if it doesn't fit, you answer your question.
Okay. And I guess I need to spend more time looking at the requirements for the project, but are we going to discuss it more?
I wasn't planning on it, but if you have questions, I'm happy to answer questions.
Okay, I'm not prepared with questions right now, but
Problem.
okay, I'll email you.
And a good place, actually, if you ask questions about the final project, if they're not specific to your data, if you
Mhm.
ask them in the forums, other people probably would love the answers to them.
Okay.
So not that I'm saying you can't ask them privately, but I know that I'm sure that everybody else in the class has the same questions you do.
Okay. I'll do that.
Okay, so are we good to stop this?
I'm good.
Okay, I'm gonna stop.